Okay, picking up where we left off yesterday, um, we had looked at this lovely graph of the Boltzmann distribution, and we were using it to interpret phase change. So we said at any given temperature, there's going to be a certain percentage of the molecules that have enough energy to overcome the intermolecular forces and undergo the phase change. And so as you get to a higher temperature, you shift this graph to the right. So you get more and more molecules that can undergo the phase change. And eventually you reach, say, the melting point or the boiling point where it's equally favorable for you to have the two phases at the same time. We can imagine this situation and how it would be different if there were stronger or weaker intermolecular forces. So on this slide, let's consider what if the intermolecular forces are stronger. How is that going to change my graph from the previous slide? All right, there's going to be less particles able to undergo the phase change. Fewer particles will be able to do it. Why? Which parameter is going to shift? The energy needed for phase change. So now, on this slide, let's say the energy needed for phase change is right here. And remember, on this x-axis is kinetic energy. So now I'd have my dotted line there, and we see with stronger intermolecular forces, I'm going to be shading a smaller number of molecules that are able to make the phase change. Actually, I don't want that in red. So if the intermolecular forces are stronger, fewer molecules can undergo the phase change. And on the next slide, we'll just consider what if the intermolecular forces are weaker. Now my energy needed for phase change, if the forces are weaker, it's going to require less energy, so my energy needed for phase change might be over here. And so even at low temperature, if the intermolecular forces are really weak, I'll still have lots and lots of molecules able to undergo the phase change. Here, I'm going to do this part in purple. Sometimes we get fancy in this class. So that's how this Maxwell-Boltzmann distribution thing relates to phase change. What questions do you have? All right. So let's consider first melting and then vaporization. I showed melting yesterday. So in melting, you're going from solid to liquid. Oh, we may need to pause for a new battery. Yep. Okay. Stay tuned. We'll be right back. We're back in business. All right, so going from solid to liquid, we said both of these are condensed phases. So when you go from solid to liquid, it's not that the molecules are spreading out all that much. In some cases, like in water, they're actually getting a little closer together. So remember, both are condensed phases. So in this transition, molecules might be spreading out a little bit, but not a ton. The big difference is in terms of order. Remember, a solid is very ordered. And a solid is going to minimize the distance between attracted parts of molecules. A liquid, on the other hand, is more disordered. And because it's more disordered, the molecules might not be on the whole much farther apart, but since they're moving more, the attracted parts don't get to be near each other as much. Okay. So water here is an interesting example. I showed this yesterday. I'll show it again today. Daniela, could you get the lights? So again, here's ice. And in ice, notice every hydrogen atom is lined up right near the lone pair of an oxygen atom. The lone pairs aren't showing. Can I show lone pairs? Yeah. So if I show lone pairs, you can see that every hydrogen atom is lined up right next to the lone pair of an oxygen atom. It's perfect arrangement for hydrogen bonding. Water molecules, it turns out, when they melt, they actually do get a little closer together. But it's no longer in such a way that all these are perfectly aligned for hydrogen bonding. That's why ice is less dense than water. That's why ice floats. But the intermolecular forces are more satisfied in the solid, in ice. So if I show hydrogen bonds again, everything's neatly arranged. In ice, there can be some vibration, but everything pretty much stays aligned where it should be. To make it easier to see, I'll change to the... Well, It won't change. Oh, that's weird. Oh well, we don't need to see the other kind of model. But if I increase the temperature, what we'll see is the molecules do actually get a little bit closer together, but now there's disorder. And so the attracted parts aren't perfectly lined up anymore. So that's melting. For vaporization, now when you go from liquid to gas, now the key difference is there's a big separation. So in both cases, the potential energy increases, whether it's melting or vaporizing. And the reason is you are separating some of the attracted particles. Okay? So in both cases, potential energy increases because here it's just the attracted parts are no longer as close as possible. From liquid to gas is a bigger change because here we're going from close together to far apart. So in this case, intermolecular forces get completely overcome. So again, potential energy increases. Ralph. So the question is about if you apply pressure to something, can you make it turn from a gas to a liquid or from a liquid to a solid? And the answer is, in most cases, yes. Putting pressure on things tends to make them denser because you force the molecules to be closer to each other. So it'll usually force it towards the most dense state. For most things, that's solid. But for water, it turns out liquid is more dense than solid. So you can melt ice by actually applying pressure to it. And people relate that to ice skating. When you ice skate, you're taking all your weight and you're putting it on a really tiny blade. So a tiny area. So lots of force, small area. That means you're applying lots of pressure. And that is partially what helps melt the ice under your skate blade. And having that little layer of melted water makes it that much slicker. So makes you glide. But most substances, that doesn't happen because the solid is more dense than the liquid. Okay, so the question is, to vaporize water, you need 100 degrees Celsius. And the answer, I have to reject the question because that statement's false. If it rained the other day, there was water on the ground. Did it ever reach 100 degrees Celsius? No. Is that water still there? Most of it's gone. All right. So vaporization actually happens at lower temperatures, and the reason is no matter what the temperature, there's always going to be some portion of the particles that are able to escape. All right. So here is a sample of, I believe, argon is what's in this simulation. And this is at, I want to say like negative 200 something degrees Celsius. What we're going to do is we're going to watch for a little bit, but we just saw a particle escape. Even at this really low temperature, this is way below its boiling point. Occasionally a particle is going to escape. What I can do is change the temperature a little bit. And if I increase the temperature, what will happen is I'll increase the amount of kinetic energy they have, and so more of them start to have enough energy to break away. But then some of them, when they come back down, don't have enough energy to bounce off, and so they stick back to the surface. If I raise the temperature, I'll increase that proportion that can break away. And you'll notice sometimes when they come back down to the surface, they bounce off. Sometimes they come back down to the surface and they stick. This is actually constantly going on anytime you have the surface of a liquid. So the puddle's outside. At the surface of the puddle, you have some water vapor molecules that will come down, hit the surface, and say, ooh, this feels good, and they'll stick to the surface. So there are some molecules condensing at any time, whereas you have other molecules in the liquid that reach the surface and have enough kinetic energy, and they break away. I also have one that's in 2D here that might better illustrate the point. So if you watch this for a little bit, you'll see there's constantly particles breaking away from the surface and joining the gas phase, and there's constantly particles in the gas phase that hit the surface and stick. Since this is a closed container, what will happen is you'll reach a point where the rates of those two processes are the same. So you have equal numbers of particles leaving the liquid and joining the liquid at any point in time. And so you end up with an equilibrium number of particles that are in the vapor phase. Okay? Question? The question is, can you see this happening under some sort of microscope? And the answer is no. I mean, molecules are way too small. So this is a model, but it's a model that works really well, makes good predictions. And so, it's one that I sort of internalize into my worldview. We can't actually see atoms, and most molecules are too small for us to actually see. But if we imagine that they are real and they are actually there, it helps us understand phenomena. So this is what we call vapor pressure. And I'm actually going to show a little flash animation that's going to repeat what I said, but maybe more eloquently and in a more robot-y voice.
This is an apparatus for measuring the vapor pressure of a liquid at a given temperature. The U-tube attached to the flask contains liquid mercury, which is used to measure a change in pressure. What happens at the molecular level during evaporation? In the beginning, the traffic is only one way. Molecules are moving from the liquid to the empty space. Soon, the molecules in the space above the liquid establish a vapor phase. As the concentration of molecules in the vapor phase increases, some molecules return to the liquid phase, a process called condensation. Eventually, the number of molecules leaving the liquid is equal to the number of molecules returning to the liquid. A state of dynamic equilibrium is reached as the rates of evaporation and condensation become equal. The difference in mercury levels, represented by H, is the equilibrium vapor pressure of the liquid at the given temperature.
Okay, so I didn't have control to be able to pause that, and there's a lot of stuff going on, so I'm going to play it again. Just to point out some of the parts. This gray stuff that, if you're watching at home, you can maybe see the cursor arrow. This gray stuff here is mercury. This tube would have a vacuum up here at the top. And so the mercury would have a tendency to reach the same height on both sides if there's nothing pushing against it. But if you have more stuff pushing on one side than the other, the mercury gets pushed up one side of the tube. The graph over here is showing that evaporation is essentially going to have a set rate, and that's based only on the temperature, the percentage of the molecules that have enough energy to break away from the liquid. So this red line for rate of evaporation, that red line stays constant because you have the same portion of your water molecules that are able to break away at any given point in time. But when you start out, if there's no molecules in the vapor, then no molecules are going to come back and condense, stick to the surface. Over time, as you get more and more molecules in the vapor, more and more of them will come back and stick, so the rate of condensation comes up until you reach a point where those two are at the same rate. So I'll play it one more time.
This is an apparatus for measuring the vapor pressure of a liquid at a given temperature. The U-tube attached to the flask contains liquid mercury, which is used to measure a change in pressure. What happens at the molecular level during evaporation? In the beginning, the traffic is only one way. Molecules are moving from the liquid to the empty space. Soon, the molecules in the space above the liquid establish a vapor phase. As the concentration of molecules in the vapor phase increases, some molecules return to the liquid phase, a process called condensation. Eventually, the number of molecules leaving the liquid is equal to the number of molecules returning to the liquid. A state of dynamic equilibrium is reached as the rates of evaporation and condensation become equal. The difference in mercury levels, represented by H, is the equilibrium vapor pressure of the liquid at the given temperature.
So again, here this is representing the same thing going on. And what we can see is if I lower the temperature, we would expect all the molecules will have less kinetic energy on average. So what will happen to the percentage that can escape the surface? It goes down. What will happen to the percentage of the vapor molecules that when they hit the surface will stick? That'll go up. So if I lower the temperature, we'll see things slow down. And over time, we're going to end up with fewer molecules in the vapor phase. It might take a little while. And the lower I make the temperature, over time, the fewer molecules will be in the vapor phase. All right. So a couple of things I want you to know about the term vapor pressure. When we say vapor pressure, there is a missing word. He used it in that little presentation. Anyone catch the missing word? The equilibrium vapor pressure. So to define vapor pressure, it's the pressure exerted by the vapor above a sample of liquid when equilibrium is reached. And we haven't used the word equilibrium so much this year. I think maybe we can turn the lights back on now. So this word equilibrium, what that means is when the rate of evaporation and the rate of condensation are equal. We'll use the term equilibrium a lot going forward this year. And it always refers to a situation where a forward and reverse process are happening at equal rates. Adam? The question is does this relate to the peak in the Maxwell-Boltzmann graph? Well, the Maxwell-Boltzmann graph, if we're thinking of vapor pressure, let's take this graph as an example. What this graph is showing is everything, let's say at the high temperature, everything in this red region, all those molecules have enough energy to break away from the surface. And so those will be molecules that, if they reach the surface, will break away and become vapor. At the same time, you'll have vapor molecules that now have a similar Maxwell-Boltzmann distribution. And everything to the left of the line, those would be molecules that when they hit the surface are going to stick. As far as mathematically where this line lies relative to the peak and how that relates to like boiling point and melting point, I don't actually know if there is a straightforward mathematical relationship. My guess is there's not. So I would think of this qualitatively, and not think of the peak as representing, some specific, really important point. All right, so I had the picture here, which was a screenshot from that little demo. And what I want to do now is think about what would this look like if I lowered the temperature. So right now I want you at your table talk about how you would fill in the picture if the temperature were lower. What changes would you make between this picture and this one where I kind of blanked stuff out? All right. Quincy, what's one change your group came up with? The evaporation rate would be lower. All right. Let's see, what color was that in? All right, so that was in red. I'll try and be consistent. So the rate of evaporation, in this case, would start lower. Fewer molecules would have enough energy to break away. Eduardo, what's another change that your group came up with? Rate of condensation would... All right, so dynamic equilibrium you think would get established more quickly? So it would start further to the left? I'm not sure if that would happen in terms of time. I'd have to actually think about that one. So we're going to have a slower rate of evaporation, which means it's going to take longer for us to establish vapor phase. I'm not sure it would change the time or if it would make it shorter or longer. I don't know. Do you have a specific argument for why? All right. I'm going to have to leave that one out there. I don't think it's necessarily wrong, but I'm not sure. The amount of time to establish equilibrium is going to depend on how long it takes for those two rates to become equal. And while I'll agree that the rate of condensation doesn't have to come up as high as it did in the previous graph, because there's going to be less vapor evaporating, it's going to be slower to gather vapor. It also is going to be slower to start condensing. And so I don't know about the amount of time to reach equilibrium. So that's a good point. That I just don't know the answer. What's another change that we could confidently predict? How about the left side of the room? Well, all right, the height will be smaller because there's going to be less vapor. So maybe it would only go up to here. So rate of evaporation lower. The height would be smaller. Max? Yeah, fewer vaporized particles. So we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in this picture. So in the new picture, maybe it would only be 6. Then the AP curriculum now is really big on you being able to make these particulate level drawings of various phenomena. So that's why we're going to focus on making those drawings a lot. When you take the practice AP test and when you look at the AP test itself, you'll probably be surprised by just how many drawings there are. And I'm going to fill in the rate of condensation down here. And like I said, I'm not sure exactly when it would reach the rate of evaporation. Or we're not sure how it would change. But the key is to recognize that the vapor pressure at equilibrium is going to be lower because you have less evaporation. All right, so to just fill some of this stuff in, as temperature goes up, we get more evaporation. So vapor pressure increases. Now, one relationship that you are expected to know, and when we cover equilibrium later in the course, this will make more sense. But when the vapor pressure equals the external pressure on the liquid, what that will mean is the vapor will boil, the liquid will boil. So the boiling point is the point at which the vapor pressure, the equilibrium vapor pressure, and the external pressure are equal. So that implies that there are two different ways I could make a liquid boil. What's the traditional way? How do you usually make a liquid boil? Heat it. So as the temperature goes up, vapor pressure goes up until vapor pressure equals the external pressure. What does this imply about a second way to make a liquid boil? So, you could keep the vapor pressure the same but lower the external pressure. Until it equals the vapor pressure. So yesterday I gave you all a sample of liquid in a syringe, and I asked you to try and compress it. So we were just looking at the fact that liquids are not compressible. Today I'll give them back out to you. What's one way I could drop the pressure inside the syringe? I could increase the volume, right? We've already seen that. So if I rapidly increase the volume, I'm going to cause the pressure inside to drop, and I can actually make my liquid boil. And I'll pass these around so you guys can do it for yourself. It doesn't get hot, but it does boil. So you can boil something at room temperature if you get the pressure low enough. So, student question, and I get this question all the time, so could you cook pasta that way? Well, what is the important part about cooking pasta? Is it important that the water is boiling? It's important that the water is hot. So this would not be a good way to cook pasta. And in fact, if you look at your box of pasta, whenever you buy a box of pasta, it might have on the side high altitude cooking directions. If you live in Denver or, I don't know, Albuquerque or Mexico City or some city that's at altitude, the external pressure is lower. And what happens is the boiling point is lower. So if you want to cook pasta at altitude, you're going to have to boil it longer because it's at a lower temperature. You can also cook things faster if you have a pressure cooker. So a pressure cooker is a closed chamber that allows the external pressure to get really high. And if the external pressure gets really high, your boiling water can get over 100 degrees Celsius. And so, you know, if you want to cook something faster than you normally would in boiling water, you can use a pressure cooker. So the question is, does this have power applications? Because in power plants, like coal plants and nuclear plants, they operate by heating up water, causing it to boil, and then using that expanding steam to push a turbine. The issue is, in order to lower the pressure, that's a less efficient way. It takes more energy to lower the pressure to get the gas to expand. So I don't think that would be an effective way to produce power. All right, so let's finally close out by talking about how intermolecular forces play into everything. Melting point and boiling point, we've just kind of addressed. So stronger intermolecular forces, in fact, I'm going to write it up here. What do stronger intermolecular forces cause? For melting point, stronger intermolecular forces are going to force the melting point in what direction? Up. Boiling point, same thing. You're going to have to heat it up more in order to make it boil. Viscosity, what is viscosity? How thick a liquid is, how much it resists flow. Viscosity is resistance to flow. So, for instance, honey is very viscous. You try and pour honey, it pours very slowly. So Julia pointed out that my little fun statement for this set of lecture notes was that this class is viscous. We stick together. That was a stroke of brilliance on my part, I think. So stronger intermolecular forces are going to make something more viscous. So the conclusion that Max is drawing is honey must have strong intermolecular forces. So honey has lots of sugar molecules and, you know, some water. We looked, I believe, at the model of sugar molecules earlier. Sugar molecules have all these oxygens bonded to hydrogens, and so they can make tons of hydrogen bonds. So yeah. All right. So this last example, I'm not going to take the time to run through it because we're short on time. But what would be your approach to answering this question? All right. So identify types of forces. And if two things have the same category of force, you're really going to have to think about what makes one have stronger forces than the other. So, for example, can you pull two out of this list that would have the same kind of forces? All right, so I heard Br2 and F2, or NaCl and Al2O3. So I'll leave it to you as a homework assignment to think about that one. But the last thing I wanted to ask was, what if I have a really big molecule like C20H42? C20H42, when I have a hydrocarbon like that, made of just hydrogen and carbon, is that going to be polar molecules or nonpolar molecules? These are going to be nonpolar molecules. You know, if I wanted to draw a skeletal structure of it, it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All right, there's my skeletal structure. So, nonpolar molecules, what kind of forces would I be looking at? Dispersion forces. Which would make you think, oh, really weak intermolecular forces. But what else can we say about this molecule? It has a really big mass. It's got lots of electrons. It's got a big surface. And sometimes dispersion forces over a really big surface can add up to making something have a really high melting point, a really high boiling point. So it's got dispersion forces only, but lots of them. And so sometimes it can be hard to figure out where that would fit in terms of melting point. And if you looked up the melting points of the things on the previous slide, and you looked up the melting point of C20H42, you might be surprised where it fits in. So we have these two things, strength of intermolecular forces or types of intermolecular forces, and then size of molecules that both end up being factors. And you'll think about that a bit on the problem set too. All right, we'll call it a day.